Okay, so now let's finally take a look at that third problem that is on that N2L or Newton's second law problem demo. You're going to find this in your OneNote. If you go into the OneNote under Content Library, then under Neerhoof Demos, it's the one that says Demo N2L Newton's second law problem. And we are on the third problem in that set. If you just scroll down, you will find it. Now, I've already drawn a little sketch in here, and if we take a look at this problem, what makes us different from the one that we did the other day is that this gives us a situation where we have an object on a ramp. So we have angles involved, and this is going to make us use our vector analysis where we break a vector down into components and all of that stuff. But let's read the problem and mark down anything in there that we find important. So a 2.5 kilogram box, already I am seeing a nice number, 2.5 kilograms, accelerates down a ramp tilted at 30 degrees to the horizontal. That's important. If the frictional force is 1.5 newtons up the ramp, how much force is pulling it down the ramp, and what is the source of this force? Okay. So, a couple of things here. I know my mass. I know the angle at which the ramp is oriented toward the horizontal. I know the frictional force, which is kind of good. And the rest of this I should be able to put together by drawing a very nice free body diagram. So I'm going to just do that kind of right here. Ooh, but first I'm going to change my pen. There we go. So I'm going to draw a free body diagram. I'm going to have my dot there to represent the box. Field forces first, so gravity. I am not going to use the feeler dealer notation. It just, I think it's easier for you to see if I don't do that on these, but you should be using that. And then I am going to go ahead and draw in any contact forces I have. Now, if I circle that box, only thing touching is that surface, so the ramp and the box. And so I'm going to have a normal force. I'm going to eyeball it at 90 degrees to the angle on the ramp. That will be my normal force. And then it does tell me I have a frictional force, and that frictional force is oriented up the ramp. And so the box wants to slide down the ramp. If it's sitting still, it is accelerating, so we know it's moving. So its direction of motion is down the ramp. That means friction is up the ramp. So I'm just going to draw a frictional force in here. And because the object's moving, I know that this is kinetic friction. Okay, and I know from the problem that the value of that force is 1.5 newtons, and that would traditionally be in that positive direction to the right. Okay, so now what I need to do is I need to calculate the rest of these forces to the best of my ability here. And so first thing I can do is I can definitely calculate FG, force of gravity. I'm going to do it right underneath the drawing here. So remember, force of gravity is always equal to mg. And that means that it is going to be equal to that 2.5 kilograms times the negative 10 meters per second squared. That's little g. So FG is negative 25 newtons. Make sure that you always keep the negatives from here on out. So I'm just going to mark this. FG, the value of FG is negative 25 newtons. And I'm just going to put that right there beside FG. And now is when I run into the place where I've got to figure out, I can't figure the normal force out directly. I'm going to have to kind of reorient myself in space, and I'm going to have to get the components of the gravitational force. to do that, we take what would normally be that XY axis, that vertical horizontal axis, and we're going to rotate it a little bit. This time we're going to go a little bit counterclockwise. And we are going to make what you would have been the y-axis. I'm just going to draw it in there. Follow the normal force. And what would have been the x-axis is going to follow the friction force. Now, what this also means is that what would have been that x-axis is now parallel to the surface of the ramp. And so many times in these problems, it's easier to talk about not x and y directions. It's easier to talk about parallel directions and perpendicular. The direction parallel to the surface of the ramp, and then the direction perpendicular. And then, so that's how I'm going to go for this problem. And so I'm going to mark these axes. I'm going to label them. That what would have been my y-axis, that's going to become the perpendicular axis. What would have been my x-axis is going to become the parallel axis. And I'm actually going to mark my vector components that way on my gravitational vector too. And you will see this is pretty common. Whatever works for you. If it helps you to keep x and y in your brain, you can always use that. If it helps you to use perpendicular and parallel, you can always use that. There's no one way that is more correct. It's only what helps you. Okay, so now what I'm going to do is I'm going to break down that gravitational vector into its components. I'm going to have a perpendicular component, and I'm going to label that FG, perpendicular, like that. Then I am going to have a parallel component, a component that's parallel the surface of the ramp. That's going to become FG parallel. And that process creates a right triangle here, and my 30-degree angle is tiny up there. All right, now, next thing I need to do is I just need to calculate the value of the perpendicular and the parallel components of gravity. And that is straight up SOHCAHTOA. I'm trying to save myself some space where I'm going to need it. Let's do it this way. I'm going to come up here. Okay, so for that FG perpendicular, remember that our kind of master formula for these components is it's going to be FG, the actual full gravitational force, times either sine or cosine of the angle theta, which is 30 degrees for us. And so the way that works out here, it's going to be FG, which is negative 25 newtons, times the perpendicular component is going to be the cosine. So cosine of the angle, which is 30 degrees. And when I put that in my calculator, I am going to end up with FG perpendicular equal to negative 21.7 newtons. And I can come over and I can put that on here. So this is now negative 21.7 newtons. Then, likewise, I am going to do the same for my parallel component. FG parallel is equal to the negative 25 newtons times sine of 30. And that is going to equal, I'm just going to save myself some space, so I'm going to do this. That's going to equal negative 12.5 newtons here. And I can put that down here. I know I'm running into tiny little spaces. Negative 12.5 newtons. Box it up. Now, always double check when you're done with this stage that your signs are correct. If I look at the actual free body diagram, both my parallel and my perpendicular components are pointing in negative directions, down and to the left. And so it makes sense, and it is very good that my numbers came out negative. It's just a kind of quick and easy way to check yourself. So for now, I'm just going to leave that be. We'll come back to those numbers and what that all means in just a moment. The final kind of question, or really the first question here, however, is if the friction force is 1.5 newtons up the ramp, how much force is pulling it down the ramp? So let's go back to our box for just a second. And let's look at things in the perpendicular direction. So I'm looking at the normal force and at then the pink perpendicular force of gravity. And notice that in that direction, the box is not moving. It's not floating up or crushing down into the ramp. And so what that tells us is that those forces are balanced. So these two forces are going to be balanced, and that means the normal force here is going to be equal to 21.7 newtons. Equal in magnitude to the perpendicular component of gravity, opposite in direction. And this also tells us, because of the magic word accelerates, we know that in that down ramp, that parallel to the ramp direction, I have unbalanced forces. And so for me to figure out exactly how much force is pulling it down the ramp, I need to write a sum of forces equation in that direction, and I need to figure out what is the total force that's acting in the downward sort of down ramp direction. So I'm just going to write a quick sum of forces. I'm going to write my sum of forces in, and that is the parallel direction. So I'm going to put the parallel direction. And that is going to be equal to those two forces that are in that direction, which is going to be my force of kinetic friction, plus it's going to be that green parallel component of the force of gravity. So FG parallel. And so if I want to know what is the total amount of force that's pulling it down the ramp, well, it's going to be sum of force in the parallel direction. The friction force is 1.5 newtons plus the gravitational force parallel to the ramp is negative 12.5 newtons. And so the sum of my forces in that parallel direction, 1.5 minus 12.5, 11 newtons in what direction? Negative. This is your answer. The force pulling it down the ramp is 11 newtons in the negative direction. And what's the source of that force? I mean, what really is the unbalanced force that's pulling it that way? The source of that force is really just that parallel component of gravity. And because that's the part of the gravity force that is actually causing the slide down the ramp. That pink perpendicular part of the gravity force is what's holding it onto the ramp, sticking it onto the ramp. Only the parallel component is causing it to slide. So, several steps. The neater you can keep your work area, the happier you're going to be, and the easier it's going to be for you to follow your own train of thought. Now that you have seen these different kinds of problems, I'd like you to go and give the problems in the formative a try.